Alright, so when we collect oxygen over water, it's best to think of this as Dalton's mixture. The total pressure in this tube is going to be equal to the pressure of the oxygen plus the pressure of the water. The pressure of the water, we just measure the temperature of the water and then we get it off the table. And so let's take a look at a sample problem here. Calculate the partial pressure of oxygen in atmospheres in the sample collected over water. Given that the total pressure of the mixture is 0.98 atmospheres, and the partial pressure of water vapor is 16.5 millimeters of mercury. And so I'm gonna modify this problem a little bit. I'm gonna give you a volume for this as well, so we can kind of visualize what's happening with this. And so, let's say I collected 1 liter of this mixture, and the pressure is not quite 1 atmosphere. Let's say the pressure is 0.98 atmospheres. It's a little bit less than an atmosphere. So we have 1 atmosphere pushing down here, there's 0.98 atmospheres pushing out here, or in here, I should say. All right, so what is the pressure of the oxygen gas? And the 0.98 atmospheres, this is going to be P total, the pressure of the mixture. And so P total, the pressure of the mixture, is equal to the pressure of the pure oxygen plus the pressure of the pure water vapor. This is gaseous water here. The pressure of the water vapor I get from a table. So that's usually given here. And they give it to us here. The partial pressure of water vapor is 16.5 millimeters of mercury. So in this case, it's 16.5 millimeters of mercury. That's how much water vapor pressure I'm going to generate. That's at a specific temperature. Well, we can figure out what temperature that is by going back to this table here. 16.5. Do you see it? What temperature it is around? Around 19 degrees C. Yeah. And so at 19 degrees C, we have 16.5 millimeters mercury. So this water sample must be at 19 degrees C. It's going to generate that much water vapor, which gives us 16.5. And so that's P total. Well, P total is 0.98 atmospheres. The units don't quite match. P of O2. So in other words, we got P of O2. The pressure of O2 is going to be P total minus the pressure of the water vapor. And so this is going to equal 0.98 atmospheres minus 16.5 millimeters mercury. So we have to convert one into the other. So which one should we convert? Let's take a look. Should we convert atmospheres to millimeters or millimeters to atmospheres? We should convert millimeters to atmospheres because they're asking for the partial pressure of oxygen in atmospheres. So if it's in atmospheres, then let's go ahead and do that over here. 760 millimeters of mercury per atmosphere. So this is going to be 0.98 atmospheres minus 16.5 divided by 760. So 16.5 divided by 760, 0.0217. It's going to be 0.0217. I've allowed 3 sig figs, so they'll carry 1 extra. 1. So 1 atmospheres. This is going to give me 0.958. So I'm going to have 0.958 atmospheres of O2. It doesn't matter what the volume is. I just chose 1 liter. It could be anything. It's just volume, whatever volume it is, half liter, 1 liter, whatever. But in that volume, okay, I chose this so we could visualize this. The way we're visualizing this is as a Dalton's law mix. And so 1 liter of mixture consists of how many liters of oxygen? How many liters of oxygen do I have in this 1 liter of mixture? I have 1 liter of oxygen at what pressure? No. 0.958 atmospheres. In other words, I'm going to get rid of all the nitrogen. Is that right? Yeah. I'm going to get rid of all the water vapor out of there. So it's just the oxygen. Well, if I get rid of all the water vapor, then there are no water vapor collisions. It's just the oxygen collisions. Okay, plus, how many liters of water vapor do I have? I have 1 liter of H2O gas. At what pressure? And so this is the way we visualize Dalton's law mixture. Now, as far as this mixture goes, I have 1 liter of oxygen, the pressure is lower. I also have 1 liter water vapor, the pressure is lower. And so how much oxygen, pure oxygen, did I collect? The amount of pure oxygen I collected is 1 liter of pure oxygen at a pressure of 0.958 atmospheres. That's how much oxygen I generated by decomposing my KClO3. Can you visualize this as an Avogadro's? Can you tell me how much oxygen did I collect, pure oxygen did I collect in an Avogadro's visualization of this mixture? I'm sorry?
Did you ask for liters?
Of oxygen, pure oxygen.
About 0.97 liters.
0.97 liters. Good. How do we get that? We just take the fraction. It could be a pressure fraction, mole fraction, whatever fraction we have, and then just times it by the total volume. And so the pressure fraction of oxygen is going to be 0.958. 0.958 out of the total. The total was 0.98. So 0.958 out of a total of 0.98. In other words, for the oxygen, the volume is equal to 0.958 over 0.98 times 1 liter. And so this is the fraction of oxygen in this volume. So I get 0.977 liters. 0.977, is that what you guys get? Okay, 0.977 liters. And so what I have here is I'm going to have 0.977 liters of oxygen. What's the pressure? 0.98 atmospheres. So to get 0.98 atmospheres, I'm going to have to shrink the size of this down a little bit, make this a little bit smaller. Smaller to compress the gas a little bit. So we'll get the same number of collisions. Oops, oxygen, red, water I made. Did I make water green? So does that make sense? You got to shrink the volume down and kick up the pressure a little bit. So it's going to be half. Okay, now what about the water vapor? How much water vapor did I collect? So again, I'm going to do the fraction. What fraction of this is water? it is 0.02171 out of a total of 0.98 times 1 liter. 0.02171 divided by 0.98 times 1 is 0.0221 liters of H2O gas. And so I'm going to have a tiny bit of H2O gas. Yeah. In other words, we could figure out the percentages. In other words, this is 97.7% oxygen, 2.2% water vapor. And the pressure of the water vapor is going to be at 0.98 atmospheres. So if I take 0.977 plus 0.221, I'm going to get 1 liter. And so the volumes are additive, the pressures are constant. Both ways are valid. So how much oxygen did you generate? Well, how much oxygen I just generated is 1 liter of oxygen at 0.958 atmospheres, or equivalently 0.977 liters of oxygen at 0.98 atmospheres. This is the exact same amount. Okay. Don't worry about it too much if this doesn't make any sense. If it doesn't make any sense, the calculations are really, really simple for Dalton's law. The calculation for Dalton's law looks like this, which looks like this. P total is the sum of the partial pressures. This kind of level of calculation that you have. But the reason I'm bringing this up is because people get confused all the time with volume and pressure. So the sooner you see it, the more time you'll have to absorb it. In Chem 1A, you'll have to have this down. Path is really well understood. Okay, so that's gas mixtures. Now we're going to deviate from gas mixtures. We're not going to talk about gas mixtures anymore. Instead, we're going to talk about solids, liquids, and gases. Okay, so solids, if we visualize the particles of a solid, like this. The solid could be either crystalline or it could be amorphous. But whatever the solid is, we look at what holds the particles together. What holds the particles together are bonds or the forces, and we'll just say or the forces of attraction between the particles. We're going to call them particles. Particles could be molecules, ions, atoms, whatever. Forces of attraction between particles, which we call the IMF. IMF stands for intermolecular forces, but particles need not be molecules. Molecular is just used as a global term to represent any kind of particle, whether it's an ion, an atom, or molecule. We'll call it molecular. But just for this, intermolecular forces, or IMFs. And so what we notice about solids is that these bonds that hold the particles together are very strong. That's why we have a solid. They're stronger than the kinetic energy, or the temperature that's trying to break them apart. So if it's a solid at room temperature, that means the bonds are quite strong, stronger than room temperature's kinetic energy. However, if it's a liquid, then the kinetic energy can actually break them apart, but not completely. they break them apart so that we have what kind of motion being introduced. Over here we have no, what type of motion? No, well, what kinds of motion are there? You guys remember? Do you remember the 3 types of motion? Wait, this is way back when. When were we talking about it? Vibrational, translational, and rotational. So solids have no translational motion. Liquids have translational motion. Solids and liquids have vibrational and rotational potential. Solids maybe, liquids for sure can rotate. But what we see here is that the IMFs, or the bonds or IMFs, bonds are stronger than these IMFs typically. Bonds are much stronger. You have covalent bonds, ionic bonds, metallic bonds. Those are much stronger than these IMFs that I'm talking about here. But the bonds or IMFs are comparable to the kinetic energy or the temperature. That's what we got. For gases, the kinetic energy is very high. So yeah, we kind of broken it apart here in a liquid, but we're going to completely break it apart in a gas. So all the particles are broken apart, and then what we see is that the bonds or IMFs are a lot weaker than the kinetic energy or temperature. Let's review some of the properties of gases. The properties of gas. Gases may be compressed or expanded even. Liquids cannot. Yeah, particles in a liquid are still touching each other. Gases expand to fill their containers, liquids do not. Gases have low density, like on the order of grams per liter. Liquids have relatively high densities, like 1,000 times greater usually. Gases may be mixed in a fixed volume, liquids cannot. Gases can be mixed in a fixed volume. That's what? Dalton's or Avogadro's? Gases can be mixed in a fixed volume. Is Dalton's or Avogadro's? That's Dalton's. When we do gas stoichiometry, we don't think that. When we do gas stoichiometry using Avogadro's, we think of 1 liter of methane plus 2 liters of oxygen gives us 3 liters of mixture. Gases exert constant pressure on the walls of their container. Uniformly in all directions, pressure in a liquid container increases with increasing depth. So these are things we talked about before. And so let's look at some properties of liquids. One property is vapor pressure, which we talked about. Vapor pressure is the, when you have a liquid like this, some of the liquid evaporates into the gas phase, and those gas phase liquid particles or molecules of water, in this case water vapor, cause collisions. Those collisions generate pressure. So that's vapor pressure. When we hit equilibrium vapor pressure, that's called 100% saturated. If it's water, we call it 100% relative humidity, the equilibrium vapor pressure. One thing we know is that some things have higher vapor pressure, some things have lower vapor pressure. It depends on how strong the intermolecular forces are. In water, they're fairly strong, but there are things that are weaker and there are things that are stronger. Things that are weaker would be like ether. Ether has very low, very weak intermolecular forces. If it has very weak intermolecular forces, it's easy to vaporize. If it's easy to vaporize, then it's going to have high vapor pressure. We call those volatile. And so something that's more volatile is easier to vaporize. Gasoline. Is gasoline easier to vaporize than water or harder to vaporize than water? Easier to vaporize than water. Therefore, it's more volatile than water. Therefore, it's got stronger or weaker intermolecular forces holding the particles together. Weaker. Maple syrup. Is maple syrup easier or harder to vaporize than water? harder. And so it's got lower vapor pressure, it's harder to vaporize. Lower vapor pressure, but stronger intermolecular forces. Here's this. In order to reach 100% relative humidity, we have to have a closed container. If we have an open container like this, then the water is just going to evaporate because it's never going to hit 100% relative humidity. It's just going to disperse out because we live in a desert. If we live in, like maybe on the East Coast, then maybe you can hit it in an open container, but you would be really miserable. If it's 100% relative humidity, it's really miserable. Why? It's really miserable because, yeah, perspiration doesn't evaporate. Right? You've reached that point. It does evaporate, but unfortunately you got condensation going on too. And you've hit that point of dynamic equilibrium where nothing's changing, but it's changing. It's changing, but it's not changing. Dynamic equilibrium. The water molecules are cycling back and forth, but there's no net change. They're just spinning wheels. Right, that's vapor pressure. The next property we're going to look at is heat of vaporization. Heat of vaporization is the energy required to vaporize. High heat of vaporization, lots of energy required to vaporize. Low heat of vaporization, a little bit of energy required to vaporize. So maple syrup, high heat of vaporization or low heat of vaporization? High. Hard to vaporize, requires a lot of energy. Ether, gasoline, low. Boiling point is the temperature at which it boils. So the stronger the intermolecular forces, the higher the temperature is required. The weaker the intermolecular forces, the lower the temperature is required. Low. When something boils, what happens? When something boils, what happens is the vapor pressure is equal to the atmospheric pressure. And so we got the vapor pressure pushing up, we have atmospheric pressure pushing down. Once those are equal, the vapor pressure is equal to that, then it starts to boil. And so what we got to do is we got to increase the vapor pressure. Increase the vapor pressure, increase it. How do we increase the vapor pressure? We increase the temperature. Let's take a quick look at this table back here. What is the atmospheric pressure in millimeters of mercury? (760). And so what we need to do is we need to keep increasing the temperature, and eventually I'm going to hit a temperature where the vapor pressure is equivalent to atmospheric pressure. Atmospheric pressure is 760, the vapor pressure is 760. Unfortunately, my table ends at 30. My table ends at 30, and I'm at 31.9 here. At 30.9, I'm at 33.6. So at what temperature do you think I'll hit 760, if any? Do you know, I know what temperature I'm going to hit 760 at, even without looking at the table. Do you know what it is? It's 100 degrees C. At 100 degrees C, this vapor pressure is going to reach 760. And that means it's going to match with atmospheric pressure, and I'm going to get boiling. So boiling is going to occur. And the vapor pressure matches. Well, when you look at a data table like this, is it easy to read data tables like this? No, a lot of people don't like data tables like this. And so they do something called data reduction. One way to reduce all these numbers down into something simpler is to do this. Rather than making it in table form, we do a graph. And it'll say, take all that data and graph it. If we take all that data and graph it, this is what we get. This is how the vapor pressure increases with temperature. and you know, I predicted at 100 degrees C, you know what I predicted the vapor pressure to be? 760. And so what we call that is, we call that the normal boiling point of water. The normal boiling point is because that's normal atmospheric pressure. But what if you have an abnormal atmospheric pressure? Will it still boil at 100 degrees C? Let's say, what is abnormal atmospheric pressure? Abnormal atmospheric pressure would be something like high altitude. At high altitudes, do you know, is atmospheric pressure higher or lower at higher altitudes? So let's say we're in Denver. Is the atmospheric pressure in Denver typically lower or higher than sea level? It turns out it's lower because, you know, you have less of a blanket. At sea level, you have the biggest atmospheric blanket, but as you climb higher and higher in elevation, you get less and less of the blanket of atmosphere, so the pressure is lower. And so what tends to happen is, okay, at sea level, water boils at 100, but if you're in Denver, Colorado, the water boils at a lower temperature. So what? Water boils at a lower temperature. That means hey, that's better, because if water boils at, let's say, 90 degrees C, then it won't take as much time to boil water. Have you tried to boil a pot of water here at sea level? It takes a long time. It's got to boil at 100 degrees C. So if water boils at 90 degrees C and it takes less time to boil water, does that mean food cooks faster? Let's say you want to boil some pasta. Is it better to boil it at 90 degrees C, or is it better to boil it at 100 degrees C? Well, yeah, okay, maybe it's going to take less time to boil water, but it's boiling at a lower temperature. You know, I'm going to continue this. Maybe at the top of Everest. Top of Everest, we're talking about maybe a third. And so water boils at maybe about 70 degrees C, something like that. Hey, water is boiling at 70 degrees C. I might as well cook my pasta at 70 degrees C rather than 100 degrees C and save some time, right? Is that good logic? Yeah. No, it's not good logic, because they'd say this. Have you heard this rule of thumb? For every 10 degrees C change, it's either going to cook it twice as fast or half as fast. In other words, you either, this is what you do. So in Denver, Colorado, they have high altitude cooking directions. High altitude cooking directions, you got to cook it longer. If it's only boiling at 90 degrees C, it's going to take twice as long to cook your pasta at 90 degrees C than at 100 degrees C. Right? And so if you live in Denver, Colorado, probably what you should do is you should get a pressure cooker. If you get a pressure cooker, then it boils maybe at a higher temperature. And so let's say it's boiling at 110 degrees C. If water is boiling at 110 degrees C, then you're going to cook things twice as fast. It's going to take half as much time. And so anyway, we have individual boiling points, which just depends on what the atmospheric pressure is, and then we have something called normal boiling point. Normal boiling point is for normal atmospheric pressure. But we could have abnormal. Abnormal atmospheric pressure would be in a pressure cooker or high altitude or something like that. It's not really abnormal, it's just different. All right, so the heat of vaporization, actually, let's see. So we graph these things. We graph it. Here. So this is the vapor pressure of water here on the right. Vapor pressure of water at 100 degrees C, it's 1 atmosphere or 760 millimeters of mercury. And so we can see, we can figure out what the boiling point of water will be at any pressure. Here. By looking at the vapor pressure, how the vapor pressure of water changes. Now, is ethanol more volatile or less volatile than water? More. Because look at a temperature like 40 degrees C, there's a lot more ethanol vapor than there is water vapor. And so ethanol is much more volatile. But diethyl ether is way more volatile because at 40 degrees C, there's no more liquid dialkyl ether. It's all boiled off. The boiling point of dialkyl ether is only 34.6. So dialkyl ether is the most volatile. So at 40 degrees C, it's all vapor. So these are different vapor pressure curves. Dialkyl ether being the most volatile, water being the least of these three, and ethanol being somewhere in the middle. Fast enough. All right, and now what we're going to do is going to look at heat of vaporization again. Heat of vaporization is the amount of energy it takes to vaporize a certain amount. So for example, water takes 44 kilojoules of energy to vaporize 18 grams of water, or about a mole of water. And so delta H of vaporization is called the enthalpy of vaporization. So if it costs you 44 kilojoules to vaporize a mole of water, 18 grams, then the reverse process is called condensation. When we condense that water from steam to liquid water, it's going to release 44 kilojoules per 18 grams. That's a lot of energy. So it's a lot of energy to boil, and a lot of energy is released when we liquefy it. And so steam burns are some of the worst, because where does all that energy go? Well, if the steam comes into contact with your skin, all that energy is going to go under your skin. Severe burn. So, delta H of vaporization. We have a few other properties that we'll talk about for water. One's viscosity. Viscosity is the resistance to flow. And so maple syrup is highly viscous. Water is a lot less viscous. Ether is even less viscous. And so the stronger the intermolecular force is, the higher the viscosity, more resistant to flow. Surface tension is the amount of energy it takes to break the surface of water. So if you have a swimming pool and you dive headfirst into water, you have to break the surface tension of water to dive in. But let's say you filled your swimming pool with maple syrup and you dove in headfirst. Would it be the same? No, that'd probably be pretty painful because maple syrup is a much higher surface tension, right? And so this is breaking the surface. Water surface tension is surprisingly high. Let's see. Have you seen this? Okay, this surface tension demo, paperclip, water. Paperclip should sink or float. Paperclip should float? Or paperclip should sink? Well, let's say this. It's going to sink, right? It's going to sink because a paperclip is more dense than water. But it floats. Why? Because of surface tension, right? Surface tension. And so the reason is, yeah, it should sink, but it costs energy to break the surface. If I pushed it into the water, it's going to sink. But you know, I can command it into the water. You want me to command it into the water? Watch this. I command the paperclip to sink. Did you see that? This is, I just did this magic wand type deal and it's sunk, right? That's pretty good. Actually, you know what this stuff is called? This stuff is called a surfactant. You know what surfactants do? Surfactants weaken the surface tension of water. And you want surfactants to weaken the surface tension of water for cleaning. Because what you don't want is you don't want water to pool up. You want water to spread out. And so, like, if you compare, let's compare Windex. If I compare Windex on the surface, it spreads out very nicely, even though Windex is mostly water, right? And so I get a very thin layer of Windex there. Whereas if I put some water there and try to spread it out, it pools up and tries to stick together. Have you noticed that? But if I put some surfactant in there, some Windex or some soap also lowers the surface tension. So I get a very thin layer of Windex here. Over here I got, a puddle of water. You can see this also in drops. What's the shape of a drop? The shape of a drop is a sphere, right, or teardrop, maybe. There's a fountain. Have you seen that fountain in downtown LA which shoots huge drops of water? They're water drops like 5 milliliters in size, and you can watch them, and you think they're going to break apart, but they don't. They try to stick together. And that's because of this. There's a difference in energy between being inside and being on the surface. Which one do you think is happier, the water molecules inside or the ones on the surface?
Inside.
The ones inside are a lot happier because they're surrounded by other water molecules. And so there are a lot of electrical attractions holding that. Whereas here, they're only being held in by these ones down here. And so surface molecules have higher energy than bulk or interior molecules. So interior molecules or bulk molecules are more stable, usually. And so to make more surface costs energy. You're going to go up in energy, so it's less favorable. Nature tends to minimize energy. All right, let's look at some of the properties. Just a quick review here of some of the properties. Ether. Ether has a very high vapor pressure, but it would have a low heat of vaporization, a low boiling point. What about viscosity? Viscosity is not shown here. Would ether have high viscosity or low viscosity? Low viscosity. Would ether have high surface tension or low surface tension? Low surface tension. Low surface. The higher the surface tension, the bigger the drop you can make. So if you compare the size of a drop of water to the size of a drop of Windex, the drop of Windex is going to be a tiny drop, whereas a drop of water is going to be a big drop. So the size of the drop depends on the surface tension. Water has a much higher surface tension, much higher viscosity, but it has a lower vapor pressure. The low vapor pressure, high heat of vaporization, high boiling point, high viscosity, high surface tension. And so it's always going to be kind of like this: low, high, 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 or high, low, 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 as far as the properties of liquid go. And then we can understand it in terms of intermolecular forces here. But we don't really pay attention to the numbers, we just pay attention to the trend in this particular slide here. And what are these intermolecular forces? We have three major types that you should know. And they're all kind of similar. We have something called the dipole force. The dipole force is attraction between the positive pole of one polar molecule and the negative pole of another molecule. And so a dipole force would look something like this. This is bromine chloride. Bromine chloride, chlorine's more electronegative, it's smaller. And we got a dipole here. So this dipole is going to be attracted to this dipole. This is the dipole for the molecule itself. The bond dipole and the molecular dipole are the same here. And so we got attractions with other molecules this way, and we got attractions with other molecules this way. The chlorines and the bromines like to line up. These are what we call permanent dipoles. These are fixed dipoles here. What if there's no dipole? What if there's no dipole? If there's no dipole, that means that nonpolar. So what holds two nonpolar molecules together? What's holding the gasoline together? Something's got to be holding the gasoline together, otherwise it's not liquid. And so what is holding gasoline together? What's holding gasoline together is what we call a temporary dipole attraction. So normally gasoline's nonpolar, or this could be helium or some other atom. Let's take these as two helium atoms. Two helium atoms are nonpolar, but that's nonpolar over time. The electrons are moving. The electrons are in constant motion. Can you pinpoint where the electrons are? No. You know, that's called the, what is that principle called? Starts with an H. The Heisenberg uncertainty principle. We don't pinpoint where the electrons are. We have some problems. The electrons are moving. Let's say both electrons in helium are up here. That's going to mean in this instant, this is a negative pole, that's a positive pole. But in the next instant, the electrons move again, and that dipole disappears. And so this is what we call a temporary dipole. These temporary dipoles are on average are no dipole. So this is zero dipole. But in this one instant in time, we've got a temporary dipole here, which means electrons here are going to be repelled by that. And so electrons here are going to be pushed to the other end. That's called an induced dipole. So this is called an instantaneous dipole. In one instant in time, we've got a dipole that's going to induce a dipole here. So instantaneous induced dipole sets up an attraction. This attraction only lives for a very short period of time and then disappears. But they break and form repeatedly, and so that there's a net attraction. It's pretty weak, but there's a net attraction overall. And so these induced dipoles, you know, instantaneous induced dipoles are very weak compared to dipole attraction. Dipole attraction is stronger. But these are the electrical attraction between molecules that produce temporary dipoles. At the opposite end, we have very strong dipoles. Very strong dipoles are called hydrogen bonds. These are very, very big dipoles. These very, very big dipoles are formed when hydrogen is bonded to nitrogen, oxygen, or fluorine. Fluorine is the most electronegative, followed by oxygen. Oxygen is number 2, nitrogen is number 3. These are the top 3 in electronegativity. The top 3 in electronegativity is going to suck all the electron cloud away from hydrogen, making this dipole bigger. The delta plus on hydrogen is big, and delta minus on fluorine is big. And so if we got big dipoles, these are unusually big dipoles. These unusually big dipoles result in pretty strong intermolecular forces. Between ammonia molecules, we can have it. Between methylamine, you know, hydrogen bonded to nitrogen. Between water, methanol, ethanol, etc., and hydrogen fluoride. Those are going to be strong dipoles. But how strong? Well, this is what they mean by strong. Okay, does methane hydrogen bond? No. But ammonia does. It's hydrogen bonded to nitrogen, and water does. And so what we see is it bucks the trend. And so this is why we say it's unusually strong, because it doesn't follow the usual trend here. So unusually strong. One thing to also see is this is methane here at the bottom. At the top of this is tin tetrahydride. Methane and tin tetrahydride are non-polar. That is, they don't have a permanent dipole. Instead, they rely on instantaneous dipole, induced dipole. And so the magnitude of the dipole, instantaneous dipole you can generate, depends on how many electrons you have in the cloud. Tin has a lot more electrons than carbon. And so tin can generate much larger instantaneous dipoles, and hence induced dipoles, than methane can. And therefore, tin, being a bigger molecule with more electrons, has stronger intermolecular forces. Now, if we have molecules of roughly the same size with the same number of electrons, then these ones are the most polar here, and this is the least polar. So polarity has an impact there. You just need to, you don't really have to study this graph much. That's it there. Next, I have to talk about the kinetic energy distribution, but what I think I'm going to end early here today. And then we'll finish this next week here.